Hello everyone. Please make sure that you have this worksheet, Functions Defined by FTC. What we're going to do today is do some application problems using FTC. So we know that FTC helps us take the integral, the definite integral of a function from a to b by using the antiderivative. Big F of b minus big F of a. So some of these problems are going to be pure math application problems like the front of this worksheet, and then some of the problems are going to be real world application problems like the back. I'm not going to work all the problems in this packet, but I'm going to do some of them. Everything that's left over is for you to practice in addition to the review sheet, which I handed out yesterday. If you didn't get one, please make sure you get a review. So for number one, we are given a function f of x that equals the integral of some other function g of t dt. We talked about yesterday when we were doing the second fundamental theorem of calculus. T is the dummy variable, and my bounds are from -4 to x. So x is the actual variable of this function, which is the upper bound is changing, and so we're trying to figure out or f would give us the integral of that function, and the area is changing as we change x. So we're also given the graph of g. So here's the graph of g. We can notice that we have these geometric shapes. This first shape would be a semicircle, and then we have a little triangle right there, and so we can use geometry to find the areas of these shapes because we don't have an actual equation for that function. Okay, so given this graph, it's asking us to find each of the following things, starting with f of -4. So just like we normally do, we're going to plug -4 into the function, but that's going to end up being the upper bound. So the lower bound is -4, we're making the upper bound -4, and that's what we're plugging in right here for x. And then we're going to write g of t dt. So t is not changing, that's my dummy variable. Okay, so this, because the bounds are the same, this should of course equal 0. That's one of our special definite integrals. For part b, f of -2, now we're going to change the upper bound to -2. So now we have to look at the graph. We're going to take the integral of this function g from -4 to -2. So let's see where that is. -4 is here, -2 goes to here. So I basically want to find the area of that region right there. We recognize half of that semicircle is a quarter circle, and so we're just using the formula for the area of a circle, which is pi r squared, and we're dividing that by 4. So what's the radius? The radius of that circle would be 2. So we are doing 1/4 pi times 2 squared. 2 squared is 4, and 1/4 of 4 pi would be pi. Alright, so again, we're just changing the upper bound and we're finding the areas. Now we're going to find f of 0. My integral is going to go from -4 to 0 of g of t dt. So now I'm going all the way to here, and I'm going to add on another quarter circle. So now I have the area of the semicircle, which means I have 2 of those, so 2 pi, or we could say half of pi r squared is 2 pi. So my area is increasing as x gets bigger. But now you notice at 0, the function dips below the x-axis. So to find f of 2, we're going to plug in 2 right here, and we're calculating the integral from -4 to 2 of this function g. So now I'm going to here. But this region down here is below the x-axis and now has a negative area. So to calculate the integral from -4 to 2, I would need to take the positive area and subtract the area of this triangle. Well, what's the area of this triangle? The base is 2, the height is 2, 2 times 2 is 4, so that has an area of 2. So I take the area of the semicircle, which was 2 pi, and I would subtract the area of that triangle, which is 2. And if we want our answers to be exact, that's it, 2 pi minus 2. Okay, making that upper bound now 4 f of 4 is going to be the integral of this function g from -4 all the way to +4. So we're continuing here. This region is still below the x-axis, so it has negative area. And we know that has an area of 2. That also has an area of 2. So I'm just going to subtract another 2 from this, and that would give me -2 minus 2 is -4. All right. Moving on, this says f prime. We know f prime means the derivative, okay? So we have to take the derivative of this integral because my function f is the integral of g from -4 to x. So to take the derivative of an integral, I am using second FTC. So I take the derivative of the upper bound, derivative of x is just 1. Then I plug the upper bound into the function, so I get 1 times g of x is g of x, minus, then I take the derivative of the lower bound. But notice my lower bound is a constant, and the derivative of a constant is 0, so that's it. For this problem, f prime of x is just g. I am taking the derivative of the antiderivative of g, so I just get that function. So if you want to remind yourself, we talked about this yesterday, second FTC, b prime f of b minus a prime f of a is how I got that. Okay, so f prime of -2, since f prime is equal to g, this is just g of -2. Again, I don't have an equation for g, but I have a graph. So if I'm looking for g of -2, I go where x is -2, and this is just going to be a point on the graph. G of -2 is +2. F prime of 0 is just going to be the same thing as g of 0. So go on the graph right here. That's at the point 0, 0. So that's going to equal 0. And then f prime of +2 would equal g of 2. And that's down here at -2. So that's my y value. All right, then the third column we have f double prime. F double prime means the second derivative of f. It also means the derivative of your derivative. Now if f prime is g, then f double prime would equal g prime. Again, I don't have an equation. All I have is this graph. So what does that mean on the graph? Well, we know derivative means slope. This is actually just asking me for the slope of the function at each of these points. So f double prime of -2 is just g prime of -2. And this is just asking me for the slopes. So let's go to -2 on the graph. And right here, what's the slope of the function? We have a rel max right there. And of course, my slope is 0. F double prime of 2 would be the same as g prime of 2, or the slope of g at 2 down here. Notice we have a pokey part. The function is non-differentiable right there, because it's a corner or a sharp turn. So this answer is actually undefined. Corner is non-differentiable. All right, f double prime of 1 would be the same as g prime of 1, or the slope of g at 1. So that is here. And there's a linear function passing through there. Hopefully you can tell the slope of that piece of the function is -1. So this column right here, since f was an integral of g, we calculated these by finding areas under the curve. And then when we took the derivative of the integral, we just get the function x. So we calculated these by just finding points on the graph of f. And then we took the second derivative, that was just the derivative of g, which these are all end up being slopes on the graph. So this is how we can think about integrals now, talking about a graph. Okay, so then we have some questions. This is going to tie in some of our former content here. On what intervals is f increasing and or decreasing? And I kind of mentioned this with the sine function as my upper bound changed. Here, instead of using sine, I'm using this weird looking piecewise. So when is f increasing and when is f decreasing? This does say justify, so we got to make sure we justify our answers. So thinking back to our extrema and graphing unit, how do we know when f is increasing? We know f is increasing when f prime is positive. How do we know when f is decreasing? That's when f prime is negative. But we've got to use g to help us out with that. So f prime for this situation is just equal to g. F prime and g are the same. So anywhere that g is positive, f will be increasing. So f would be increasing. Again, here's a graph of g. Where's g positive? It is above the x-axis right here from -4 to 0. So f is going to be increasing from -4 to 0. And then f prime will be negative, again, where g is negative. So on this graph, that's where the function is below the x-axis, and that happens from 0 to 4. So that tells us that f will be decreasing from 0 to 4. And that makes sense because I start my clock, the area keeps increasing until I get to here. Now the area is decreasing that whole time. Okay, where does f have an absolute max or min? And where are the relative maximum and minimum? So we're going to have to do some tests. To find the absolute extremes, we need to do the candidates test. The candidates test, we find all of our candidates, we put it in the table. We've got x and f of x and some type of extrema. So what are my candidates? Remember, my candidates are either endpoints or critical points. Okay, so the endpoints would be -4 and 4. And my critical points are any place where the derivative equals 0 or is undefined. So that happens at negative, where does that happen? Well, let's see. It's where f prime equals 0 or does not exist. And for this problem, f prime is the same as g. So where does g equal 0 or does not exist? And that happens at 0. So here and here and here are all the places where g equals 0 or where f prime equals 0. So that's at -4 and 0 and 4. So I'm going to put 0. Those are my candidates. Then I'm going to plug those into f and calculate. And then, of course, my absolute max and min would just be the biggest and smallest of those. Now, we've already done this up here. Yay, how nice. F of -4 was 0. F of 0 was 2 pi. And f of 4 was 2 pi minus 4. So which of those is the biggest? Well, that's about 6.28. 6.28 minus 4 is about 2.28, and that's 0. So this would be my abs max. This would be my abs min. This would be nothing. Okay, so there's my absolute max and absolute min. This is a continuous function on a closed interval, so we are guaranteed to have both. Where are the relative maximum and minimum values? So the relative max is where f prime changes sign from positive to negative. But for this problem, it's where g changes sign from positive to negative. This is the graph of g, changes sign from positive to negative right here at 0. And then I already did this up here. F of 0 is 2 pi. So there's my max. Rel min is when f prime changes sign from negative to positive, or in this case where g changes signs from negative to positive. And notice it's down here and it never goes back up, so there is no place where that happens, and we don't have a relative min. So there's my rel max, and I have no relative minimum. Fun. Okay, on what intervals is f concave up and concave down? F is concave up whenever f double prime is positive. F is concave down whenever f double prime is negative. In the context of this problem, f double prime is the same as g prime. So we got to think about this now, the slopes of g. So to do our test for concavity, we need our possible points of inflection. And that's where the second derivative equals 0 or does not exist. So in this case, where is g prime equal to 0 or does not exist? What we're looking for is on that graph of g, where is the slope of g equals 0 or undefined? Well, looking at the slopes, the slope is undefined at -2, undefined here at 0 because of the corner. It's undefined at 2 because of the corner, so the slopes are undefined at those 3 places. We're not including those endpoints there. So x equals -2 and 0 and 2. So our test for concavity, we're going from -4 to 4. 0, -2, and 2 are my PPOI, my PPOI. And so I'm testing those in F double prime to check if F is concave up or concave down. Now again, F double prime equals G prime. So we pick a number like -3 and plug it into F double prime or G prime. What's the slope of G at -3? The slope of G at -3 right here is a positive number, so that's positive. What's the slope in between here at -1? The slope is negative. From 0 to 2, the slope is negative. From 2 to 4, the slope is positive. So then above that, that tells me concave up, concave down, concave down, concave up. So F is concave up from -4 to -2 and from 2 to 4. F is concave down from -2 to 0 and from 0 to 2. Sorry, I don't know what that is. Okay, points of inflection. Are any of those possible points of inflection actual points of inflection? And for that to be true, remember F double prime has to change sign and equal 0. So definitely not here, doesn't change sign, but at both of those 2 places, the function, the second derivative changes sign. So at -2 and at +2. And then of course, if you want the point, you're going back up to the top right here to pull those values out. So that's pi, and a +2 is 2 pi minus 2. Okay, why did we do all that? We did all that so that we could graph a function of f. This is a graph of g. F equals the integral of g from -4 to x. And so we have now some points that we can plot. We know where f is increasing and decreasing. We know what the extrema are for f and the concavity and points of inflection are. So we're going to put that all together and we're going to graph f down here. Okay, so let's plot those points. -4, 0. I also have the point -2 pi. Pi is about 3.14. Again, I'm just plotting all these points. I have the point 0, 2 pi, 2, 2 pi minus 2, and 4, 2 pi minus 4. And I'm plotting those all down here. So at 0, we had 2 pi, which is like 6.28. I'm sorry, that went off the graph. At 2, we have 2 pi minus 2 is about 4.28. And at 4, we have 2 pi minus 4, which is about 2.28. Okay, so f has to pass through those 3 points. What else do we know? We know that f is increasing from -4 to 0 and decreasing from 0 to 4. Okay, no duh. We have an absolute max at -4, 0. I'm sorry, we have an absolute min at -4, 0 and an absolute max at 0, 2 pi. Okay, that's my min, that's my max. Also, again, no duh. We have a rel max here. Yes, yes. Okay, so the concavity. Concave up increasing, concave down increasing, concave down decreasing, concave up decreasing. So that's gonna kind of look like that, and then go like that, and then like that, and like that. And I mean, and then that's the best that we can do to draw that graph. Woo, are you having fun? I am. Okay, turn to the second page. Number 2 is more practice of the same thing, so I'm going to leave that for you to practice. Let's look at number 4 is really important. Number 4 will be similar to what you'll see on your assessment next week. So it says if f of 1 is 12, f prime is continuous, and the integral of f prime from 1 to 4 is 17, what is the value of f of 4? Okay, so f of 4 is what we're trying to calculate. Right here it says the integral of f prime from 1 to 4 is 17. We know that if you're taking a definite integral, that means area, right? So this is the area under f prime from 1 to 4 is 17. Okay, well, let's write that down. So the integral of f prime of x dx from 1 to 4. Let's use FTC on that. So we're going to take the antiderivative of f prime. The antiderivative would just be f of x. The derivative goes away. And we're evaluating that from 1 to 4. And then we plug in the upper bound, so f of 4 minus f of 1. So this equals f of 4 minus f of 1. But they also tell us that this equals 17. So f of 4 minus f of 1 has to equal 17. And we are looking for f of 4. We need another piece of information. Right here it says f of 1 is 12. F of 1 is 12. So if I plug 12 in for that, 17 equals f of 4 minus 12. And to get f of 4, I would just add the 12 over here with the 17, making f of 4 equal to 29. So if you know one of these two y values, you can subtract it or add it to the area to get the other one. So like if I knew the lower bound, I could add it to the area to get the upper bound. If I knew the upper bound, I could subtract the lower bound and then subtract the area from the upper bound. And that would give me the same thing. So that's going to be really important for your assessment. Okay, now I want you to turn to the back of the packet. Let's look at a real-world application of FTC. Amusement parks, we like amusement parks, Disney, Universal. We have right here the rate at which people enter an amusement park on a given day, and it's modeled by this function, big E of t equals 300 E, that says 0.20 t. So it says E of t is measured in people per hour, and t is measured in hours after midnight. So E of t is measured in people per hour, so it is a rate. It is a rate of change, people per hour. And little t is time. And for this problem, time is hours after midnight. So if t equals 2, that would be 2 a.m., 2 hours after midnight. This function is valid for t between 9 and 21. Between 9 and 21. It says at time t equals 9, there are no people in the park. So first of all, if this problem is only valid for t 9 to 21, what does that mean? Of course, this is 9 hours after midnight would be what time? 9 a.m. And 21 hours after midnight would be 9 p.m. So t has to be between 9 a.m. and 9 p.m. Basically, those are the park hours for the amusement park. The park hours. Okay? All right, now it says at time t equals 9, there are no people in the park. Why would that be? When I start my clock at t equals 9, there are no people in the park? Well, that's of course because that's when the park is opening, so nobody has been able to come into the park yet. Okay, but as soon as they open the doors at 9 a.m., here come the people rushing. And if you're like me and my family, we're like running to the back of the park to go to the biggest roller coaster, because that's usually the one with the longest line. Okay, so we're going to find the integral of E of t from 9 to 12. Let's plug that function in here, which is 300 e to the 0.20 t, and we're integrating with respect to time. So we're going to use FTC to solve this. Okay, that 300 could come out of the integral because it's a constant multiple. So we're going from 9 to 12. E to the 0.20 t dt. Now we have an exponential function here, so we're going to have to use u substitution. We're going to let u equal the 0.20 t because that's the exponent. Take the derivative of that. You just get 0.20, and then we need the dt. We have the dt, we're missing the 0.20 or the 0.2, right? So I'm going to put the 0.2 in there, 0.2, and that means I need to divide the outside by also by 0.2. Okay, what else do I have to do with this definite integral when I use u sub? If you said convert your bounds, you're correct. We got to convert the bounds. So we're going to take the 9 and the 12, and we're going to plug those into this equation right here. So I need u of 9 and u of 12. You might want to pause the video and grab a calculator if you don't have one. So I need a fifth of 12, and I need a fifth of 9. 0.2 is 1/5. That gives me a lower bound of 1.8 and an upper bound of 2.4. Okay, so I'm going to rewrite my integral. 300 divided by a fifth, or times 5, is 1500. And now my new bounds are going from 1.8 to 2.4. 1.8 to 2.4. Then I can rewrite this as e to the u du. Of course, we've all forgotten our integrals. The integral of e to the u is just e to the u. So this is 1500 e to the u. And then we're going to keep with the new bounds. You don't have to go back to the t's at all because my answer is just going to be a number. Okay, using FTC, this is 1500 times e to the 2.4 minus e to the 1.8. So at this point, you want to grab your calculator and type that in. And I'm going to round to the nearest whole number, 7,460, because my question is, what's the unit? Remember that this E is measured in people per hour, and time is measured in hours. So if we multiply people per hour times hours, this is in people. This is in people. So that's the answer to part A. Now, I want to know what that means. 7,460 people did what? What did they do? Who are they? Okay, if you come down here to part D, it says using correct units, explain the meaning of that. What did we just find? What is the integral of e of t from 9 to 12? Well, we know 9 means 9 a.m., 12 in this situation would be noon, and we got a total number of people. So that's the total number of people. Number of people that have what? E stands for enter. That have entered the park. That have entered the park from 9 a.m. till 12 p.m., which is noon. So in the first 3 hours that the park is open, this is the total number of people that have entered the park. Question, does that mean that this number is how many people are in the park at noon? No, it is not. Why is that not the total number of people in the park at noon? And the answer is because people leave. People start leaving. I don't know why they're leaving. Maybe they left something in their car. Maybe, the baby needs a nap, whatever. But people are coming in and now people are starting to leave. So this is just the total number of people that have entered the park in those first 3 hours. It doesn't mean that that's the total number of people that are in the park at noon. Okay? Well, at the same rate that people are coming in, people are also leaving. If people were leaving the amusement park at a rate capital L of t, again, L of t is measured in people per hour, write a calculus statement in terms of E and L to calculate the number of people that are actually physically in the park at any given time from 9 to 12 noon. Well, we just said right here that if you take the integral of E from 9 to 12, that's the total number of people in the park that have entered the park in the first 3 hours. But we have to take away all the people that have left. How many people have left? Well, they're leaving at a rate of L of t. So in those first 3 hours, This would be the total number of people that have left the park. So if you subtract the number that have entered minus the number that have left, of course, that difference will give you the number of people that are actually in the park at any given time in those first 3 hours. So because the bounds are the same and the variable of integration is the same, we can, of course, combine those together and write E of t minus L of t et. But that's as far as we can go because we don't know what L is. Okay. Next question, find the average rate. Find the average rate at which people are entering the amusement park. Okay, so we've got our formula, which was for f of c, but this is going to be e of c. Again, it's a y value. Your formula for f of c is 1 over b minus a times the integral of f of x dx from a to b. So in this problem, instead of f, it's a big E. So what's your A and your B? Your A and your B, we're going from 9 to noon. The number of people that have entered the park is the same as this. That's your E of t dt. But then we just basically have to divide it by the length of time. How many hours passed between 9 a.m. and noon? Of course, that is 3 hours. So 12 minus 9 is 3, and we're just taking a third of the number of people. So if this many people have entered the park in the first 3 hours, then the average rate would just be that total divided by the 3 hours. So this would be 1/3 of the answer we got for this problem, which is 7,460 people, and that is approximately equal to 2,487. Now this is a rate, so this is in people per hour. Now, did every hour have exactly 2,487 people come in each hour? No, it changes, right? But this is the average. This is the average rate that people are coming into the park. Okay, so hopefully that helps you understand average value a little bit as well. And then part C says to use a trapezoidal approximation with 4 equal subintervals to estimate that. And you can try that if you want to practice your trapezoid rule. And I have the rest of the key to this in Schoology. I would recommend maybe trying this Coca-Cola application problem on your own. To practice what we just did on the back, because it's doing the same thing. Find the rate, what does it mean, average, trapezoid. So this is a good review kind of everything mixed together using application problems. Okay. Notice here, S equals CE to the KT. So it's a population question. The difference is now it's a definite integral, and I can calculate the values with the definite integral. Okay, so the rest of this, again, the key to this whole worksheet is in Schoology, so you can do these other problems for practice. And please make sure that you complete all of your homework in my math lab.